And we're live.
Good evening, everyone. Thanks for joining tonight. Before we get started on this session on the multi-barrier system, I'd like to take a moment to acknowledge the traditional territory on which we're hosting this. I personally am broadcasting from the City of Toronto, which is sited on the traditional territory of many First Nations, including the Mississauga of the Credit, the Anishinaabe, Chippewa, the Haudenosaunee, and the Wendat people. It is currently home to many diverse First Nation, Inuit, and Métis people. And I invite you all to consider the traditional territory on the land where you're watching this session from. And hopefully we can all work to be better stewards of the land. Next, please. Thanks again for joining us. My name is Peter Keach. I'm one of the lead researchers on the multi-barrier system, which is the subject of tonight's session. I'll give you a little background about me. 9 years of experience at NWMO already, researching state-of-the-art methods of containing nuclear waste and protecting people and the environment. Prior to being at NWMO, I actually worked on the NWMO project at the University of Western Ontario for about 6 years on this project and a few others. Currently, my team and I work with a lot of international colleagues on the best practices for managing nuclear waste. We have lots and lots of collaborations on those, and we do a few world-leading methods or technologies of our own. I've also worked as an environmental auditor, working on how to safely deal with land. Of course, that's quite relevant to my current role. I am a corrosion expert, and I'm one of the world's leaders in nuclear waste. And of course, this is very relevant to how we will keep people and the environment safe. And I'm presenting tonight with my colleague and friend, Sarah Hirschhorn, who is going to speak now. Next, please.
Hey, thanks, Pete, and good evening, everyone. My name is Sarah Hirschorn. My background is in geochemistry, which is essentially looking at how things move and behave in groundwater. I've been with the NWMO for just over 12 years now, and as Director of Geoscience, I'm working with the team that is studying and learning about the rock that will surround our repository. The rock or the geosphere that we will select works with other materials, both natural and engineered, to form the multiple barrier system that we're going to be talking about today. Maybe I'll turn it back over to you, Pete, to start us off.
Thanks, Sarah. Welcome everyone. And this is the second information session that the NWMO has held to introduce ourselves to the South Bruce community. As many people are aware, South Bruce is one of the 2 locations remaining for Canada's deep geological repository. In the last session, this is like our last session in that it's not a face-to-face meeting, which we would ordinarily be conducting. And although the COVID-19 situation is improving, we're still not ready to do those yet. We hope that we'll be able to do that very shortly, of course. As I mentioned already, we're talking about the multiple barrier system tonight, which is 5 separate barriers that help keep people in the environment safe, basically permanently. And then at the end, we'll do a question session as well. Next, please. The last session was a basic introduction to the project, why we're building it, and why we look at South Bruce. There was some discussion on what nuclear fuel is, what used nuclear fuel is, and why we need a permanent solution. We talked a bit about the timeline and the process for site selection, and then we covered some aspects of safety and the principles that we use to ensure safety within the project. Next, please. And we'll continue to discuss safety in tonight's session, but with some specific discussion on the multiple barrier system, because that is really the heart of how we are going to protect people and the environment for the long term. So I'm really hoping that this session helps people understand how we achieve safety, and particularly, as we'd like to call it, passive safety, which means that this system will remain safe without any future human intervention. Next, please. And I'll get Sarah to do this slide.
Okay, thanks, Pete. I think this slide is really a good summary for our discussion on the multiple barrier system. It's really an illustration of the whole deep geological repository concept. The diagram includes a look at the surface where we have things like the facilities where the used fuel will be packaged into the long-lived containers. And it also shows how the repository will look underground, where it will be constructed 500 meters or more below ground surface. You can see in the middle of the diagram, there's a series of placement rooms where the used nuclear fuel containers surrounded by the bentonite clay buffer will be placed and ultimately sealed in the host rock formation. This concept of a deep geologic repository is being pursued by all countries that have nuclear power programs as the approach for managing used nuclear fuel for the long term. And really by long term, we mean, a million-year kind of time frame, which is really forever from a human perspective. And the reason that all of these countries are looking at deep geological repositories is because it is the best method to ensure passive safety for people in the environment, not just today, but for generations to come into the future. Next slide, please. So today, Pete and I are going to talk about one part of the deep geological repository, and that's really what it looks like underground and the concept of the multiple barrier system. The multiple barrier system is basically exactly what it sounds like, the series of barriers, 5 of them, that include engineered and natural barriers that will work together to protect people and the environment over the long term. Because each of these barriers serve to contain and isolate in their own right, we can do things like look at worst case or hypothetical unlikely scenarios and say, okay, if this barrier doesn't behave as expected, or if it completely disappears, how do the remaining barriers behave? Next slide, please. We're going to take a look tonight at each of these barriers one by one, but just before we do that, I wanted to show an example of how we can see these barriers existing in nature and how we can learn from their behavior in these environments over the long term. This slide is showing a cartoon of the Cigar Lake uranium deposit in Saskatchewan, which many of you have probably heard of. Cigar Lake is one of the richest uranium deposits in the world. It was formed about 1.3 billion years ago. And the thing that's really interesting for us is that when this ore was deposited, it was surrounded, naturally, not by humans, by a clay formation, which you see in yellow in this cartoon here. So you have the uranium ore surrounded by the clay, surrounded by the host rock, and in this case, the host rock is not technically as good as the host rock we're looking for a repository, because in this example, the rock is a type that allows groundwater to flow through it. But even in this example where you don't have the greatest rock barrier, the radiation of that uranium ore deposit with the clay surrounding the deposit contained and isolated the radiation from the surface environment for that 1.3 billion years. So examples like these let us see how the barrier materials that we're using in a repository can work, and it lets us see that over geological time. So we started here sort of looking at the overall repository concept, but now we'll go with a bit closer look one by one of each of those 5 barriers that make up the multiple barrier system. Next slide, please. So the first barrier is the actual fuel pellet itself. These pellets are made from a uranium dioxide powder, like what's being mined at the Cigar Lake mine we just looked at. This powder gets baked in a furnace to produce a hard ceramic. And you can see in the picture the pellet's about as tall as a quarter. As you know, and you can imagine when you think of washing your dishes, ceramics are a durable material. They don't readily dissolve in water. Now, obviously, the form of the fuel itself was designed for their life in the reactor, but that stability of the pellet is also a benefit to us when we're talking about long-term management. And now I will turn things back over to you, Pete, to talk about some of the other barriers.
Thanks, Sarah. So with the fuel pellets, you can see in this picture that the pellets are put into long tubes in a material that's a zirconium alloy known as zircaloy. So that's a very strong and corrosion-resistant material. It actually is very durable even in the harsh environment of a nuclear reactor. So even though, as Sarah mentioned, the nuclear fuel, uranium or uranium oxide, is not easy to corrode, this provides an additional layer of protection against corrosion. And of course, the important part about that is what prevents the movement of radioactive materials, is that it is an ability to prevent corrosion. Next slide, please. But a significant amount of our work in engineering, it goes into this particular one. This is a schematic of the used fuel container. So the bundles are put into this in the used fuel packaging plant that was shown on the schematic earlier. And this is a large, durable container, and it's designed for the long-term storage of nuclear materials. So the containers themselves are made from carbon steel, which is for strength, and I'll talk about that in a minute. But the outside is what I want to highlight because it is coated with copper, and that is the corrosion-resistant material that we use to prevent water from getting inside the container, which helps keep the radioactive materials inside. And so the idea of this container is to prevent any radioactive materials from getting out until the decay allows the radioactivity level to go back to natural uranium. And when we talk about this is where we talk about the million-year sort of concept. I'll talk a little bit more about copper on the next slide and why we know it's so long-lived. But there's also another part about the container that's important, and that's thank you. It is the fact that it's very strong. So these containers are designed to withstand future glaciation events. And we've done some testing at the Penn State University lab where they test U.S. submarines. Extreme conditions, the equivalent of being more than 4 kilometers underwater. So that's the sort of pressure that would crush some submarines. And when we take our container into those facilities and test them, they easily pass. So we do know that these containers will be strong enough to withstand the forces of glaciation. Next, please. This is the slide that you just got a quick preview of. This is our slide that helps to support, again, Sarah showed the natural analog of the repository earlier, and this is our natural analog for copper. And these are samples in the top 2 images there that you see. On the left is one from Ontario, close to Sault Ste. Marie, and then Michigan. It's all part of the same geological formation. And it's over 1 billion years old. And within the rock itself, the copper is isolated and has remained as metal for basically for more than 1 billion years. So in the right environment, you can actually find copper in the ground as metal, which is how we know that it's not subject to corrosion in the underground processes. And then in the next slide, I will talk about clay, but I have one here to show copper within clay. And this is the bottom picture, and it's from England. It's copper that has been embedded in clay and sat in the mudstone for over 200 million years. And again, you can see the metallic copper showing through the clay. So both of these are extremely long-lived samples that allow us to be certain that copper is the right material to prevent corrosion in the underground. Next, please. So I talked about clay on the last one, but I'll really get into it here because that's our next barrier. It's a clay exterior that we will use. And you can see it in this schematic here, the pictures where it's labeled bentonite clay. And it's bentonite for some very important reasons. So bentonite is a naturally occurring material, but it's a swelling clay, which is what makes it special. So when it gets exposed to water, it will grow and swell, and it will fill up any voids or cracks that might be in the repository. And so that's one of its primary uses is as a sealing material. Bentonite is very stable. Natural formations are hundreds of millions of years old. And just a little bit on the specifics of this picture. So right close to the container, we'll have a very dense type of clay. We actually form it into a block and then carve out a shape for the container. So that's in the white in the picture there. And then all around the outside of that, we put another form of bentonite. It's a granulated powder type form, and we pack it in everywhere that is between the container, the buffer boxes is what we call the container packages, and the walls itself. So we pack it in extremely tightly, and so that will eventually, if it gets wet, it will seal and prevent water from flowing, like was shown in the Cigar Lake example. And water can only move by very slow processes called diffusion. So there's no free-flowing water at repository level. And that is very important for preventing water getting inward or any radioactive material getting out. In the event of, as Sarah mentioned earlier, we do these assumptions where we assume that a barrier is missing, and then we can probe the safety of the system for that. Next slide, please. And back to Sarah.
Thanks, Pete. Like the copper that Pete just talked about, bentonite clay is one of the barriers in the repository, not just because of the science and lab studies, but because we've been able to see how bentonite has worked in this exact way over geological time. We've already talked about the Cigar Lake example, and this is another one here on your screen. In this picture, you see trees that had been buried in clay about 1.5 million years ago, again, buried naturally, not by people. And the key thing is here, you're not looking at a picture of fossilized wood. These are the actual tree stumps that haven't been decomposed or aren't petrified wood. And the reason for that is that the clay that surrounded the trees prevented the movement of water carrying any oxygen from reaching them. And so because the clay did seal off these trees and keep them isolated from the environment, they didn't decompose, but really remained as they were when they were buried. Next slide, please. So the final barrier that we talk about is the geosphere, or the host rock itself. The repository will be constructed 500 meters or more below ground surface, and just for context is about 3 times deeper than the deepest point of Lake Huron. The work that NWMO is doing as part of our site investigation activities, so things like borehole drilling, is so that we can understand the characteristics of the geosphere, the rock and the water, deep below ground, to ensure that when we select a site, we're picking one that can contain and isolate the used nuclear fuel and will protect people in the environment now and into the future. Next slide, please. When we think about what makes a host rock suitable, it's all the things you see listed on the slide here. But really, if we had to summarize it in a word, it's probably stability. Whether we're in crystalline rock, like we're studying in the Ignace area, or sedimentary rock, like we have in South Bruce, the geosphere really is the host for the repository, and it will act to protect and isolate the repository from things like destructive natural events, so whether that's earthquakes or future ice ages or erosion. The geosphere that we would site a repository in will have minimal water movement at depth and no known economically exploitable natural resources at depth. There's a bunch of reasons why we don't want those things at repository depth, but a simple example is to minimize the risk of future human intrusion. So you can imagine thousands of years into the future, you don't want people inadvertently drilling into the repository as they're looking for those resources at depth. As we mentioned, the repository will be constructed 500 meters or more below ground surface, depending on the geology of the site that is selected. In the South Bruce area, we know the potential host rock formation, which is called the Coburg Limestone, is about 650 meters below ground surface. Hard for me to say it as a geologist, but at the end of the day, we're basically looking for boring rock that doesn't have resources at depth, rock that doesn't have water flowing at depth, rock that is stable and predictable and relatively homogeneous. Next slide, please. So we're close to the end of our presentation for tonight, which really focused on the underground part of the repository and the multiple barrier system. But we know there have been questions in South Bruce about what's happening above ground with respect to the land that we're acquiring for the repository. It's really a whole topic unto itself, and while we aren't covering the details of that today, I did want to mention that we'll be discussing this aspect in much more detail in the fall for those of you who are interested. But in the meantime, we did want to clarify what will happen to the land that we're acquiring as part of the site selection process. So for the underground footprint of the repository, we'll need about 1,500 acres of land. But for the facilities at surface, we need much less, about 250 acres. So the rest of that 150 acres at the surface would continue to be kept in use as it is, so mostly as active farmland. And maybe with that, I will turn it back to you, Pete, to wrap things up.
Thanks, Sarah. So that's a summary of the 5 multiple barriers that are working together within the repository. And now we're happy to move to the question and answer session of tonight's presentation. And we just would, there's been a mailer recently in South Bruce, and there were some inaccuracies, and we think that there's probably been some questions raised about that, and we're really happy to try and address some of those inaccuracies. So if you have a question, this is the time to do it. We do have a few that have been generated already, but this is the time to please send them in, and we promise we'll get to as many as we can in the time that the moderator allows us to do that. But we do, of course, want to be respectful of everybody's time. And we did have a late start, but we'll do our best to get to as many questions as we can. So I'll move on to the next slide, if possible, where I think there is a question. Yep. Okay, so the question, how will our local water resources be protected when the repository is built? So I think this one's best suited for you, Sarah.
Okay, thanks, Pete. I think, what...
Before you do, I just to clarify, I want to make sure people know how to ask questions. There's a Q&A tab on the right-hand side of the page. That's where you submit your questions. Sorry about that, Sarah.
Water is a topic that obviously a lot of people are interested in, so I'm glad we have a chance to talk a bit about how water resources will be protected once the repository is built. I think, as we've seen in tonight's presentation, the design of the repository has these multiple different barriers that are really acting to minimize the movement of water. We're able to look at examples of these in nature, whether it's the Cigar Lake uranium deposit or the copper examples that Pete talked about, and we can see how these barrier materials behave and how they can protect or isolate over geological time. So really right from the form of the fuel, that ceramic that doesn't easily dissolve, to the copper-coated container, to the bentonite clay that surrounds it and fills in the repository, to the actual host rock for the repository, all of those things are acting to keep the used fuel isolated from water resources. And if we look at the South Bruce area in particular, we know that water moves extremely slowly in the rock at depth in this area. There's very, very little water in the potential host rock, and this water moves so slowly that it would take about 300,000 years for it to travel 1 meter. So really having these thick, low permeability rock formations at depth really act to isolate the repository from the shallower rock formations and from any associated groundwater or water resources that are present in the hundreds of meters above.
Okay, thanks, Sarah. Move on to the next question of the previously received questions. So, will the canisters or the repository leak and require a cleanup? So we know that this was a concern that was part of the mailer, and we do want to really put this to rest. First of all, the concept of the deep geological storage, as we've mentioned already, is the international best practice. And there's lots of countries that are exploring this, and there's huge container programs going on all over the world. And they're all slightly different because they have different, geologies and different fuels and things like that. But they all have the same basic purpose, which is to work to isolate the used nuclear fuel from people in the environment. Of course, the container, I mentioned this earlier, its job is to prevent water from getting in, and talked a little bit earlier about how important the structural features are. So the steel is there for strength, the copper is there for corrosion resistance. And we know that natural copper, is a very long-lived material. We have really good geological evidence of that. And then we have a very, very good collection of more than 30 years of laboratory results from studies, including in the underground, of copper to show that it is not going to corrode. So the containers themselves they're very carefully designed to prevent corrosion, so that they contain the fuel, the used fuel, and they prevent water from getting in. So that's why we're very confident in that. But again, as this is multiple barriers, we also have the clay and all of the other barriers. So in the event of again, when we do these scenarios where we remove barriers, we can demonstrate through our models as well as our experiments that things like bentonite work very well to seal the repository and seal the used nuclear materials in and prevent water from getting in. So those are the reasons that we're confident that there will not be problems with the canisters. Okay, next question we have from earlier. How will the used fuel be monitored after the repository is decommissioned? Maybe you can talk a little bit about this, Sarah.
Okay, sure. Thanks, Pete. So I guess first we think of the construction and operation of the repository, which will take several decades, during which time monitoring, whether it's groundwater monitoring or monitoring seismicity, or environmental monitoring will all be ongoing. And then following operations, there would be an extended period of monitoring. In our plans, we've assumed 70 years of monitoring, but really at that time, the host community in collaboration with the regulators will decide, it's many decades out from now, the exact form and length of that monitoring period. And I think this is also a good example of how the adaptive phase management approach works that we're implementing. So we don't want to prescribe now in 2020 exactly what monitoring tool will be used by future generations 100 years from now, because we know technology is going to evolve. So those kind of details will be decided collaboratively as the closure date of the repository approaches.
Yeah, and I can add to that a little bit. I mean, I talk to researchers that are doing sensor analysis currently, and we have watching briefs and regularly correspond with people that are developing advanced sensors. So we are active in the area as well, even though this is something that's many, many decades away. Okay, next question. Will the transportation of the used fuel and the operations of the repository be safe? Okay, so this isn't a talk on transportation, although we realize it's very important, and this is something that we will certainly address in other presentations. In the meantime, I'll just comment a little bit about the record of transportation. So it's a very regulated issue. There's been many, many years, more than 50 years of transportation of nuclear materials. Tens of thousands of shipments worldwide, and there have never been any injuries, accidents, or bad environmental consequences from radiation during transportation, even when there have been any incidents along the way, like accidents, because the packages are designed to prevent that during transportation. Again, this is something that our transportation team will be happy to address on how we address that. The operations, on the other hand, is another thing that we can comment on. They'll be very safe as well. That we can rely on the nuclear industry as well for its demonstration of how safe operations are in nuclear facilities in Canada. They're held to a very high degree of safety, and those are what we are going to be doing. And I'll comment as well on the technical aspects of the operations. We've put a lot of effort into keeping them as simple as possible. The packages will be assembled in the above ground facility, so the containers will be loaded and they will be welded shut and finish the copper coating, and then they will be in place already in the buffer box, so in those big blocks that were shown in that diagram earlier. So much of that happens above ground, where you can very well actively monitor things, and then they're lowered down and put into the repository emplacement room and filled very quickly. So the idea is to turn the nuclear materials around very quickly and get them into the DGR with as few operations as possible and as quickly as possible. Okay, so that's that question, and I think we have another one that has come in now that these ones are done. So this one has just come in. The moderator has just sent me a question. Can heat build up in the repository and create cracks in the surrounding rock? Okay, so let me start on that one, I think. So within the repository rooms, the containers are spaced far apart so that the heat that's generated during the radioactive decay it doesn't get very hot on an individual container. So this is designed that the peak temperature will only be around 100 degrees. And so when we look at the container materials like the steel and the copper, there's no ill effects from the temperature on that, and that goes for the bentonite clay as well. They can go through cycles easily of that temperature. We've got lots of lab results for that. So we do know that all of the materials within the emplacement rooms are very tolerant to the relatively small heat that is generated. Maybe you can comment on the rock, please, Sarah.
Yeah, sure. Thanks, Pete. I think you've mostly covered it, but again, with the spacing of the containers and the maximum heat being relatively low in the context of the geosphere, we wouldn't see any impact on the host rock for those temperatures, which in geological time is just a blip of temperature on the timescales that we're looking at.
Okay, thank you. Okay, another question is coming in live. This one is, how can this man-made technology last for the tens of thousands of years necessary for nuclear waste to become inert? Okay, and so I think it's a question that has come up a lot during the time I've talked to people, and I think it's partly answered by the fact that we're not just relying on man-made technology. We are very much relying on what we showed earlier, the analogs, the fact that clay, as a natural material lasts, uh, you know, basically forever. It doesn't alter. Thousands or millions of years are the clay deposits, and then we already showed a little bit about the copper, how it can last, in the right environment, the underground environment, it can last more than 1 billion years. So we're relying on those material properties, which we can learn about from nature. And then, of course, we have very robust engineering and laboratory programs to use those materials in a particular way, like the shape of the container. But really, we're relying on the inherent properties of those materials. Okay. Do you want to comment any further on that, Sarah?
I think you covered it well, Pete. I think the obviously the repository itself is a man-made or a woman-made, an engineered system using natural materials and engineered materials. But the concept of how these materials, the clay and the copper, work together to contain and isolate is very much based on what we see in nature.
Okay. Okay, so we have another question here. So this one is, if the site is in South Bruce, and that's a positive note, I suppose, how many jobs will be created and what is the timeline for this project? So, this is a bit far afield from our topic tonight, and it's not really either my area or Sarah's area. Although I do work a bit with the engineering team, and so there are obvious things that will be required for the repository, like working, making the containers, sealing them, managing the above ground facility. There are things like the bentonite, all of the operations that are required to put this material into the containers and underground. That's during operations. Prior to that, there's a significant impact of the construction. I'm not sure if you have any specific numbers, Sarah, on those operations.
Yeah, not specific numbers in terms of jobs, but if we look at construction and operations, we're talking decades and significant numbers of direct jobs, and then obviously much larger numbers of additional incidental jobs related to all of that activity.
Yeah, yeah, and so we can't really answer the specific number, but we'll certainly take this back and we'll get some people that are better qualified for this to give more input on this. Okay, let me see. Having a little bit of a lag on my screen here, but let me check the time. We're getting close to the end of this as well. I'm not sure if there's any last questions that we have to answer. Okay, sorry, this is in a weird color too. What is the upstream relationship between the construction of a project like this and the potential expansion of nuclear power production? Well, I guess we don't make decisions on the future Ontario. Like it's certainly well outside our mandate, and that was one of the reasons NWMO was formed as a separate entity, because it really creates a whole separate division that's only responsible for one aspect, which is the nuclear waste. So we really don't have any say on that. If there is further decisions on expanded nuclear operations in Ontario, that is part of our mandate to handle that. Our program is adaptive phase management, so we are ready to take any instruction on that from the Ontario government or whoever makes a decision on how the future grid of Ontario will evolve. So we can deal with it, but we don't really have any control over. Okay, well, I think we're getting short on time. We were supposed to be on till about 7:45, and we're getting close to that now. So I guess I would like to thank again everybody that came. I'm not sure if there's any further slides in here that we have. I don't think so. I think it's just the final one, which invites you, if you wouldn't mind skipping ahead to the find out more. Thank you. So this is our final slide where we invite anybody to send any further questions they have for topics on this. And again, we've tried our best on subjects that aren't in our area, and hopefully we've given some input, but we're happy to find the experts on those within the NWMO to give more complete answers. So again, use these addresses, the learn more address, all of these things, and we're happy to continue to work with the community and answer all of the questions that may come up. So I'd like to thank you, Sarah, for helping me out through this presentation. It was a lot of fun for me. We've never done something like this, so I hope you enjoyed it too. And thank you for all of the audience members that participated.
Thank you.